All right, so let's start the next video about ViZDoom. So far what we've done is we have, well, let's revise what we've done, right? So, well, let's run what we have so far. I can't really put runs actually. I don't remember if we left it in a state where it actually runs. Let's see how what happens. Okay, so we left it in the state where, all right, we've calculated the loss, but we didn't back-propagate the loss yet. So let's just get rid of the bit that makes it crash, and let's run what we have, and then we'll just like revise quickly what we have. All right, so it's running. We don't have a display. Let's just turn on the display so that we see the display. So if we change the set something, set, oh yeah, set window visible. Let's set that to true. We'll try rerunning it. And so now we've got this other interface. So basically, it's kind of like randomly moving around. It's sampling actions. So our model is sampling actions based on the visual input which we're giving it. So we're giving the model the frame each time, like how that frame looks. We're converting that into a torch tensor, feeding that through a convolutional network. The convolutional network feeds into a linear layer. The linear layer has three outputs, and then according to which output we're going to choose to move left to right or to fire. Now we're not argmaxing the outputs, so we're sampling from the outputs. So let's just revise briefly the code. Let's set this back to false while we remember. All right, and also let's copy this to number 5. So the last one was part 4, right? And let's copy it into, because I'm going to make these available in a GitHub repository called YouTube demos. So this one is going to be ViZDoom 5. And you can get the script as it was at the start of this video before we changed anything. If you go to the GitHub repo and you open ViZDoom part 4, why did I open part 4? I need to open part 5, right? All right. So at the moment, this is equal to part 4, and then we're going to modify it. So what we got here is we've got, well, so ViZDoom itself, just to revise, ViZDoom is a reinforcement learning environment that's been created from the Doom game. And what it does is it lets you create machine learning models such using PyTorch or TensorFlow or your favorite framework or whatever you want. Really, it doesn't have to be using neural networks. It could be using Sklearn or whatever. Create some sort of model, some sort of controller. Doesn't have to be machine learning. That's going to control the game. And what we're doing is we're creating a neural network controller using PyTorch and using a reinforcement learning algorithm called policy gradients, or otherwise known as reinforce. All right. So basically, our model gets given the visual input, and it has to produce an action at each frame. It sees how the game looks, and it has to produce an action for that frame. And then the next frame, it sees the new frame, how it looks, and makes a new action. So the game image arrives here. So we basically got this neural network model called net. It has some convolutional layers, has a couple of pullings, and it has a linear layer that's going to choose the action. And in the forward, we pass through the convolutional layers, and then we pass through that linear layer to get the action. So this takes as input like the image, like this X is an image, and the output is it's not a distribution over actions, but it's sort of a vector where each number is like the more positive the number, the more likely I was to choose that action. So the first number is maybe move left, the second number is move right, and the third one is fire. Here's the 3 actions here that we choose from. Each row is a single action that we can choose. All right, so here's our game loop. So we loop it over episodes, and then for each episode we have steps or frames. I'm going to call them steps. So each episode comprises multiple steps. Each step we're going to get the screen buffer, convert that into a torch tensor, and then we pass it through our model. We get logits out. We pass it to a softmax to get probabilities. We're going to give the probabilities to a categorical distribution, and we're going to sample from that, and that is the action that we're going to give to the game, and the game is going to give us a reward, right? And then we're also, for the reinforce, we collect this thing called logprop action, and we're going to append those to a list each frame, So that's this list up here. And then at the end of each episode, we're basically going to get the total reward we received over the entire episode. So each step in the episode, we might get -1, or if we shoot the monster, we get 100. So total reward, if we shoot the monster, we might get like -1 20 times and then plus 100. So we might get like a reward of 80 or something like that. If we don't shoot the monster, probably get a reward of like -200. The total reward, we're then going to assign equally to all of the steps that contributed to that reward. So if there's like 20 steps like moving left and then 1 step pressing fire, each of those steps is earned, so that's a total reward of 80. So the reward for each step is going to be 80. And then we're going to use that to calculate our loss. So we've calculated our loss. So we've basically like there's a formula. So basically we take log probs, multiply by the reward, take the sum over those, and that is our loss. So that's where we got to. That loss was from, like, we can find it if we go to the torch.orgs, pytorch.org/docs, and we go to distributions, and we got this formula here. So this is going to calculate our loss using policy gradients reinforce. So we've calculated at each step the m.logprob action without the negative, and then at the end of the episode, we're going to sum all those up, and that gets our loss. So the loss, we're calculating the loss on a per episode basis, and then the next thing is we're going to do the backward. So we're going to do the backward now. So we haven't done the backward yet. We've calculated this. We've got our loss. We're printing our loss, but we haven't actually backpropped it. So we're not actually learning yet. So for each episode, we're getting our total reward, we're getting our loss, but we haven't backpropped it. So let's backprop it. So to backprop it, we're going to need to create an optimizer, and we're going to have to do like opt.zeroGrad and opt.step. So let's do that. Let's like remove some of this because I don't think we need all this really. I guess we can keep that. I guess we can leave some of that in. Yes, we can leave some of that in. All right, so let's create our optimizer. So we'll create our optimizer just after creating the model. So we're going to do optim. Let's use, so I'm not going to use Adam because Adam is sometimes unstable in reinforcement learning. So let's use RMS prop, which I find, it sort of depends. Like sometimes Adam works better, sometimes RMS prop works better. Let's try one of them. So all right, so we're going to have a learning rate. So what learning rate shall we use? So let's set that at the top. So let's say, I don't know, like li equal 0, 1. I don't know. We'll see what happens. I guess we can try bigger. Don't really know. I don't really know what will work. We'll try stuff and see what happens. So learning rate. We have to pass the parameters into it. So we're going to do the net not parameters. And there's our optimizer. So we're using RMS prop. And then here in the game loop, so after calculating the loss, so we're going to do opt.zeroGrad, and then loss.backward, and then opt.step. All right, so now it stands a chance of learning. Yeah, and I guess we can just print the loss each time. Maybe we'll do loss.item, like %4f or something like that. That just removes this bit so that we just get the number. All right, so I guess we can try running it. We're going to need to do more than like one episode, right? So let's say episodes is like, I don't know, 100,000 or something, a million. It's just going to run. Actually, maybe we'll just do like wild true. So we start off with, so the moment it's being called I, and we'll just add 1 each time. I think there's like a special thing you can use actually, like where you don't have to like add 1 yourself, but I can't remember what it is. Maybe like, I don't know, maybe it's in functors or something. All right, so we're going to run part 5. So let's bring this down here. Oh, we're already printing the episode, so why would we print it again? And actually, let's like combine these lines together. So total reward, we'll also print the loss. All right, let's try that. All right, so let's try running that, see what happens. We're probably going to have to run, normally I have to run for like tens of thousands of episodes. So I might have to like start this on an instance and then go away for a day and see how it looks. All right. So what line is that? Line 189. 189. This one, right? Yeah, because it's been called model. All right. So we're getting rewards and losses. Um, all right. That doesn't seem good. Like the loss has gone to like zero, near zero, but the rewards are all over the place. That's kind of strange, right? Let's see what's going on. I have no idea what's going on. Like, I assume we need to make our learning rate smaller or something. Or maybe we need to add in a baseline, or I have really no idea. So let's just try turning this on and having a look. Okay, so basically it seems to be like just doing the same thing each time, which seems odd really, right? Let's try let's try making our learning rate smaller, see if that helps. All right, so now it's sort of continuing to explore and do random and not just like stupidly like just press left all the time. So that seems better. Um, and yeah, I don't know why the loss went to zero before, even though it was obviously. Why would the loss be zero when the? It's kind of strange. I'm not sure I understand. Anyway, so the loss should. Oh, right, because this is more positive than this. So this is actually the zero loss is worse than this because this is negative, right? Right. We want the loss to get more negative. Um, yeah, so it's not doing anything crazy now. It's sort of behaving itself. So let's turn off the view so that it runs faster. And then we probably just need to leave it to run for absolutely ages. So where do we turn? Oh, set this to full thread. So we should probably also start recording to a log file or something, right? Um, like we could use like Lightning or TensorFlow, but I normally just write to a JSON file because I'm kind of lazy. Yeah, so we can't really tell what's going on here. We need to start graphing it. So let's start graphing this. So let's have like an output file and I don't know, like log.txt and yeah. And then we're just going to write a JSON dictionary each episode. So here we're going to do like out f.write and then we'll do json.dumps and then here we're going to put a dictionary. So let's import JSON. Like, I should probably be using like TensorFlow or something, but like I look like TensorBoard, but I'm kind of lazy and just do it like this. All right, so we'll put the episode, which will be I, right? And we can put like the loss, which will be lost item, and we'll put the reward, which will be this. All right, and then we have to like add a line feed. All right. Oh, and then let's flush it. Otherwise, it doesn't write very often. All right, so yeah, all right. So let's just run that, and all right, and then we probably need like something to graph that, right? So we can use like matplotlib. So let's call it like I don't know graph log or something like that. So import matplotlib.pyplot as plot and import JSON, and I guess we can do import argparse. And if we can do like if name equal main, and then parser equal argparse dot argument parser, and args equal parser dot parse args, and then and then run args, and then here we can have def run args, and then here we're gonna here we're gonna have parser dot add argument in log file type equals str default equal what was it, log.txt. So with open args.in log file as f, and then log lines array for line in f, row equal json dot loads line, and then I don't know, like log line, let's call this log rows dot append row, and then we can print that. So the loss is becoming more positive again, right? Which is, it's sort of all over the place. It's noisy, so it's really hard to tell. I mean, that's kind of the point, right? So let's run this. All right, pym activate ViZDoom. All right, so yeah, and let's plot some graph. So I guess we need like episodes, and we need, what are we going to plot? Loss, right? For row. Oh, then we can do, I guess we can do for row in log rows, and here we're going to do like row episode, and here we're going to do row loss, something like that. Print episodes, and print losses. All right, that seems fine. All right, so let's graph this now. So plot episodes losses, and then I kind of, I don't really like using show actually, so we're just going to save this as like graph.png, something like that. All right, so if we run that, it's just going to write a file and we can open it like this. Oops. But you could also do like plot.show. All right, so that's super noisy. So let's like average out or something like that. Yeah, this is probably why I should use TensorBoard, although then it would do the averaging for me, right? So let's try that. I mean, it's pretty unclear what's happening, but we probably need to leave it for a while. So I probably should start an instance and run this on an instance, but we need to convert that into CUDA. So let's do that in the next video. So in the next video, we're going to CUDAize this, start an Amazon instance, start this running, and then just like leave it to run for a while. All right, so let's just run this for a while, like a day or two. I'm going to run this on an instance, but I guess you guys have your own computer to run it on. Let me know in the comments if you want me to show how to run it on an AWS instance. But I'm going to go off and run this on an instance now. So Doom uses the CPU, so I don't think there's any point in CUDAizing this particularly because it's going to be CPU limited, and especially because our batch size is 1. If we could run like multiple Doom instances in parallel, then we could use a batch size greater than 1, and then a convolutional network would run fast on CUDA. But like since Doom itself, I don't think can use the graphics card because it's like so old and it's before like the time of graphics cards. And our batch size is 1. I don't think there's any point in CUDAizing this. At least we might get a small benefit, but like I'm just going to run it on a CPU instance and see what happens. So let's run this and leave it for a while and see what happens. And I'll see you in the next video.